Okay, so let's start. Uh, Welcome to week 10's problem solving session. Normally, these sessions are conducted on Saturdays from 4 to 6 p.m., but this Saturday I was not well, so the session was postponed to today. So, as usual, what we'll do is we'll first solve some problems from week 10's assignment and related problems, and then the last half an hour or 45 minutes, we'll solve some problems from week 11's content. Okay, so let's start. So the first problem is as follows. Let Pk is equal to G, comma Q, comma small g, comma H be the public key and Sk is equal to X equals to the discrete log of H with base G with the secret key of the Elgamal encryption scheme. So here we are looking at the Elgamal encryption scheme. So G over here is a cyclic group of order Q. Small g is a generator of capital G, and H is going to be G to the alpha for some alpha. Okay, it would be in this case alpha is X. Yeah. So this is our public key, and this is our secret key. Now the problem is as follows: let a PPT, that is a probabilistic polynomial time adversary, obtain a ciphertext C is equal to C1, C2 of some unknown plain text M encrypted using the above public key Pk. The adversary picks a random R prime from ZQ and computes the ciphertext C prime, which is equal to C1 times G to the R prime, comma C2 times M prime times H to the R prime. The question is, what will C prime yield upon decryption? The options are M prime to the M. Option B is M plus M prime. Option C is M to the M prime. And option D is M times M prime. So let us see what C prime on decryption would yield. So recall that in the Elgamal encryption scheme. So in the Elgamal scheme, the message run is encrypted as S is equal to C1, C2, where C1 is equal to G to the beta for some beta picked uniformly at random from ZQ. Q, recall, is the order of the group, and C2 is equal to M times H to the beta. So now, what do we have? We have C prime is equal to, okay, now, so let me say that C1 prime is equal, let C prime be C1 prime comma C2 prime, then C1 prime is equal to C1 times G to the R prime is equal to uh, G to the beta times G to the R prime is equal to G to the beta prime, where beta prime is equal to beta times R prime, and C2 prime is equal to C2 times N times H to the R prime, oh, times M prime. So C2 is M times H to the beta times M prime times H to the R. Was, uh, missed G to the beta plus R prime is equal to this. Yeah, and this is equals to M times M prime times H to the beta plus R prime is equals to M times M prime times H to the beta prime. Okay, now how is decryption done? To decrypt C prime, comma, the receiver computes C2 prime times C1 prime to the minus alpha. So this is equal to, okay, so what is C2 prime? C2 prime is M times M prime times H to the beta prime times G to the beta prime, G to the minus alpha beta prime, because uh, C1 prime is G to the beta prime, and that raised to minus alpha is just G to the minus beta prime times alpha. Now, recall that in the Elgamal, oh wait, over here, our secret key is X, not alpha. Yeah, so over here, our secret key is X. Yeah, so this is to the X. Let me write secret key over here. That would be easier. And over here, our secret key is X. So, what what is H? Well, the discrete log of H base G is X, so H is G to the X. So this is M times M prime times, oh sorry, G to the X beta prime times G to the minus X beta prime. So these two are inverses of each other. So this gives us M times M prime. So the decrypted message is option D, M times M prime. Yeah, so that's the first problem. So let's look at the second problem. So the first problem dealt with algebra encryption scheme. The second problem is about the RSA encryption scheme. And the problem is as follows. Suppose in the RSA crypto system, we have NE. Recall that in the RSA encryption system, the public key is N comma E. E is that, this E over here is that E. Yeah, suppose in the RSA crypto system, we have a public key E, which has at least one zero in its binary representation. Now let E prime be another RSA public key obtained by flipping one of the zeros in E21. And the question is, uh, E and E prime are, then which of the following options are true? Option A is E and E prime are not co-prime. Option B is E prime will be even. Option C is E and E prime will be co-prime. And option D is cannot determine cannot determine the relationship between E and E prime. So let's see which of these are correct. At first sight, it might appear that since we are just flipping 0 in E to obtain E prime, they, it should be difficult to obtain a co-prime or not co-prime relationship between E and E prime. So at first sight, it might appear that option D is correct, but as we'll see, that's not the case. So okay, yeah, let's see. Okay, yeah. So we'll show that option C is correct. That is E and E prime are co-prime. Let's see why. So let uh, G be the GCD of E and E. Then uh, it is easy to see that G must divide the number. Okay, G must divide by the absolute value of E minus E prime. Now, since prime is obtained from E by flipping one of the zeros in its binary representation to one, uh, absolute value of E minus E prime looks like 1 followed by a bunch of zeros. Why? Because so let's say we excuse me. Yeah. So let's say we flip the rth bit of E to obtain E prime, then all the bits other than the rth bit are exactly the same. So when we subtract E from E prime, what we would get is that that bit, the rth bit of the resulting number would be 1, all other bits are 0. In particular, E minus E prime equals to E, uh, the absolute value of E minus E prime is equal to 2 to the I. That is, it's a power of 2. Whereas, of course, some I written it to 0, some I in N. Okay, now only numbers dividing 2 to the I are powers of 2, smaller than I. Powers of to up to I. Hence, G is equals to 2 to the J for some 0 less than equals to J less than equals to I. Okay, as G is equal to GCD of E comma E prime. G also divides E and however, as E is part of an RSA public key, E is co-prime to phi of n. Now, phi of n is going to be p minus 1 q minus 1, where p and q are primes. Now, at least one of now there is only one even prime too. So at least one of the p and q has to be odd. So at least one of the p minus 1 and q minus 1 has to be even, right? Therefore, since at least phi n is even, as the GCD of E and phi n is equal to 1, this means that E is odd. And the only power of 2 that divides E is 2 to the 0 equals to 1. Now, since G divides E, this means that as G is equal to GCD of P and E prime, we get the, yeah. So E option C is correct. E and E prime are co-prime. The option C immediately rules out option D and option A. What about option B? So uh, it is possible. Okay, so for option B, E prime is also a public key, also part of a public key. An RSA public key uh, N comma N. So just like E, E prime must also be odd. And since option B says that E prime will be even, option B is false. So the only correct option is C. Okay, so now that was the second problem. Now let's look at the third problem. So the third problem is as follows. Choose the correct options. The options are A, A, key generation in case of Elgamal requires fewer values to be computed as compared to RSA. Option B is Elgamal when instantiated with elliptic curves provides better security with smaller key length than RSA. Option C is sharing Elgamal public parameters with more than one receiver is insecure. And option D is Elgamal scheme is only CMA secure but not CPA secure. So let's go over all the options and see which one is correct. So option A is key generation in the case of Elgamal requires fewer values to be computed as compared to RSA. Well, this is true because recall that in the Elgamal encryption scheme, to generate a key, all we had to do was pick an alpha uniformly at random from ZQ, and that alpha would be our secret key, and G to the alpha would be our public key. So we only had to compute a random alpha and G to the alpha. On the other hand, in the case of RSA, to compute a public key, we have to first find out two relatively large prime numbers P and Q, then multiply them to get N, and also multiply P minus 1 and Q minus 1 to obtain phi N. So that's already four values. Then we have to find an E, which is relatively prime to phi N, and finally compute D such that ED equals to 1 mod phi N. That is, D is the multiplicative inverse of E mod phi N. So to generate an RSA key, we have to uh, compute P, Q, N, phi N, E, and D. That is six numbers as opposed to just two elements, one number alpha and one value G to the alpha for Algamar. So option A is correct. Option B is Algamar when instantiated with elliptic curves provides better security with smaller key length than RSA. This is true. Option C is sharing Elgamal public parameters with more than one receiver is insecure. No, so Elgamal is just like RSA. Elgamal is also a public key encryption scheme. So we can share the public parameters or the public key with more than one receiver, then Elgamal would still be secure. So option C is false. And option D is Elgamal scheme is only CUA secure, not CPA secure. This is also false because uh, in so Elgamal is a public key encryption scheme, and in the public key settings, CUA security implies CPA security. So it is not possible for any public key encryption scheme to be CUA secure but not CPA secure. In particular, it is not possible for Elgamal to be CUA secure and not CPA secure. And in fact, we saw in class that if the group is such that the DDH assumption holds in that group, then Elgamal is indeed CUA secure and therefore also CPA secure. So option D is also false. So now let's look at the fourth problem. So the fourth problem is as follows. It's about the Diffie-Hellman key exchange. In particular, we are going to consider a modified version of Diffie-Hellman key exchange and argue whether it's secure or not. So the problem is as follows. Consider the following modification The Diffie-Hellman key exchange protocol executed over a cyclic group of order Q with generator G. The sender and receiver send messages Ks equals to G to the X and Kr equals to G to the R to each other, where X and Y are picked uniformly at random from ZQ. And the final key that the key exchange outputs is Ks times Kr. So recall that in the Diffie-Hellman key exchange, the final key output would be Ks to the Y, and which would also be equals to Kr to the X. But in this case, we are just going to to obtain the final key, we are just going to multiply Ks and Kr. Now assume that the D log, that is discrete log, CDS, that is computational Diffie-Hellman, and DDS, that is decisional Diffie-Hellman, or our assumptions are all true in the underlying group, and this protocol is executed in the presence of a semi-honest PPT adversary. Then, which of the following options is correct? The options are: the adversary completely knows, this should be knows, yeah, the adversary completely knows the underlying output key. Option B is, uh, from the viewpoint of the adversary, the output key is uniformly random and unknown. Option C is, from the viewpoint of the adversary, the output key is pseudo-random. And option D is none of the above. So let's see which of these is correct. I don't have a space. Let me add a page. Yeah. So here's the key exchange that we see in the uh, here's the key exchange that we have in the question. Sender picks a uniformly random element from ZQ. So does the receiver. Oh, yeah, using R for random as well as receivers. Let me use script S and script R here to avoid confusion. Yeah. So sender and receiver pick uniformly random values from ZQ. Then they both send KS is equals to G to the X. And yeah, and KR is equals to G to the X. Yeah, and the key is KS times KR. KS times KR. Now this is executed in presence of a semi-honest adversary. So any semi-honest adversary can see KS and KR and can thus compute KS times KR efficiently. Yeah, so now let's look at the options. Option A is the adversary completely knows the underlying output key. That is true. All it has to do is multiply KS and KR. Option B is From the viewpoint of the adversary, the output key is uniformly random and unknown. Well, it's the adversary knows the key, so it's no longer uniformly random. It's the distribution of the output key is point mass, with the mass being on the key, and it's the key is also not unknown, so B is false. From the viewpoint of the adversary, the output key is pseudo-random. Well, no, the adversary knows the key, and the distribution of the key is point mass, with the mass being all the mass being on the key. So C is also false, and D is none of the above, which is also false because A is true. Yeah, so the only correct option is A. Now let's look at the next problem. So in this problem, we are going to look at the hybrid encryption paradigm. The problem is which of the following is or are true for the hybrid encryption scheme using KEM-DEM paradigm, that is key exchange mechanism, data exchange mechanism paradigm. Option A is if the key exchange mechanism or KEM as well as the encryption scheme are both COA secure, then the overall hybrid scheme is CPA secure. Option B is the first component of the ciphertext produced by the hybrid encryption algorithm consists of an encryption of the symmetric key under the public key. Option C is at the receiver's end, two operations happen, decapsulation followed by symmetric key encryption. And option D is the GEN, that is the key generation algorithm in KEM generates one key to be used in the encryption of the plain text. So now let's look at which options are correct. Let's go the options again. Option A is if the KEM and encryption scheme are both COA secure. Recall that in the public key settings, COA security implies CPA security. So yeah, if KEM and encryption scheme are both CPA secure, then the overall hybrid scheme is also CPA secure. Yes, this is true. We saw this in class. So is option B is the first component of the ciphertext produced by the hybrid encryption algorithm consists of an encryption of the symmetric key under the public key. Well, this is false. The correct option would be this. The correct statement is this. The first part of the ciphertext is a D is an encapsulation and not an encryption of the yeah. So uh, in this option, if the word encryption had been replaced by encapsulation, then it would have been true. But it's yeah, it's not encryption, so it's false. Option C is at the receiver's end, two operations happen. Decapsulation followed by a symmetric key encryption. This is also false. Uh, the receiver performs decapsulation followed by symmetric key decryption. Yeah. So in option C, if the word encryption had been replaced by decryption, then it would have been correct. But option C as it is false. Okay. So C is also false. Let's look at D. The Gen algorithm of in KEM generates one key to be used in the encryption of the plain text. This is false because the Gen algorithm outputs the public key and secret. Yeah, so uh, all B, C, and D are false. A is the only correct option. Now let's look at the sixth problem. Sixth problem is as follows. Which of the following statements is or are correct? Option A is in the CCA security model, the adversary can make a decryption oracle query for any message of their choice. Option B is in the public key setting, COA security implies CPA security. Option C is in the public key setting, COA security implies CCA security. Option D is in the public key setting, CCA security implies CCA multi-security. Recall that CCA multi-security is CCA security for multiple messages. So in the corresponding security experiment, instead of sending two messages M1 and M2, the adversary sends two vectors of messages M1 and M2. So let's go over all the options and see which are correct. Option A is the CCA security model. The adversary can make a decryption oracle query for any message of their choice. Well, this is almost correct. Uh, in the CCA security model, recall that there are pre-challenge training phase and a post-challenge training phase, right? So in the pre-challenge training phase, the statement is true. The adversary can make a decryption oracle query for any message of their choice. However, in the challenge phase, the adversary sends two messages M1 and M2 and receives the ciphertext C for one of the two messages at random. Okay, let's call this ciphertext C star. Now recall that in the post-challenge training phase, the adversary can make a decryption oracle service for almost every message except one message, and that message is C star. That is, the adversary cannot make a decryption oracle query for the ciphertext that is received during the challenge phase. And this makes sense, right? Because if the adversary could make a decryption oracle query for C star, then it would know by when it gets the answer, it would know whether M1 was decrypted or M2 was decrypted. So you can always win the security experiment with probability 1 and the experiment would be meaningless. It would be meaningless to define CCS security using that experiment. So statement A is not quite true. It's almost true because the adversary cannot, in the post-challenge training phase, the adversary cannot make decryption oracles query for the ciphertext that they receive during the challenge phase. So A is false. Option B is in the public key setting, COA security implies CPA security. Well, this is true because COA security and excuse me. Yeah. So in the public key settings, COA security implies CPA security because they are exactly the same. Why? Because recall the difference between the COA security and CPA security game. In the COA security game, the adversary can just send two messages M0 and M1 during the challenge phase and would get ciphertext of one of those messages at random. On the other hand, in the CPA security game, there is a pre-challenge and a post-challenge training phase. And in both of these both of these training phases, the adversary gets Oracle access to the encryption Oracle. So it gets encryption Oracle service. However, in the public key setting, how is encryption performed? The encryption is performed using the public key, and adversary has public key right. So the adversary can always get encryption Oracle service for free. Let M be the message whose encryption whose corresponding ciphertext they want. All the adversary has to do is encrypt M on its own, which it can do efficiently because it knows the public key. So yeah, in the public key setting, even in the COA security game, The adversary has Oracle access to the encryption Oracle, and so the CO security game becomes the CPA security. So CO security and CPA security are exactly the same in the public key setting. So B is true. Now let's look at option C. Option C is the public key setting. COA security implies CCA security. Well, this is false. And in fact, we saw that the Elgamal encryption scheme is CPA secure, but Elgamal encryption scheme as it is, it's not CCA secure. So yeah, there exists at least one encryption scheme which is COA secure but not CCA secure. So COA security cannot imply CCA security. So C is false. Finally, in option D, we have that in the public key setting, CCA security implies CCA merge security. Well, this is true. And this was also true in the private key setting. So D is also true. So B and D are true and A and C are false. Now let's look at the seventh problem. In this problem, we'll calculate Euler-Gaussian functions for numbers which are not of the form P times Q. So we know that the Euler-Gaussian function for a number of the form P times Q, and where P and Q are both primes, is P minus 1 times Q minus 1. And in this problem, we are asked that if n equals to P to the R1 times Q to the R2 for prime numbers P and Q and R1 and R2 natural numbers, then what is phi n? That is, what is the number of, yeah, that is, what is this phi n set n defined as 1 to n that are co-prime to n. So this is equals to n, that is the size of this set, minus the number of numbers a such that GCD of a and n is not equals to 1. That is all the numbers which are not co-prime to n. Now Q are primes. GCD of a comma n for any must be a multiple of at least one P and Q. Thus, this set is exactly the same as this A and so A such that A, or rather let me write it A and N such that or Q divides A. Yeah, let me call this one from 1 I equals to n minus size of this set. P divides A or Q divides. Hmm. Yeah, let me call this. Now, this set is the same as the set A. So this set is a union of two sets. Since there is an or over here, it's a union of these two sets. A means such that P divides A union A n such that Q divides from the inclusion exclusion principle. Size of uh, A n that P divides uh, Q divides is equal to size of A n P divides A plus A n such that Q divides A minus size of the intersection of the two sets. Yeah, but the size of the but this intersection set, okay, is exactly just let me write it down. Size of A1 P divides A size of A1 such that Q divides minus this intersection set is exactly okay. Let me call this set S1, this set S2, and this set S3. Then size of S1. Okay, let me write this then any must look like P, 2P, 3P. So, okay, so every element in S1 is a multiple of P, right? So it must look like M times P for some P. The question is, so the smallest value of M is 1. So it can go from 1, 2, 3, and so on. The question is, what's the largest value of M? Well, we know that A is less than equals to N, and for M equals to P to the R1 minus 1 times Q to the R2, M times P would exactly be N, right? So this can go on up to P to the R1 minus 1 times Q to the R2 times P. Uh, so the size of S1 is equals to P to the R1 minus 1 times Q to the R2. Because if you look over here, the first multiple was 1, the second multiple was 2, the third was 3, and the last one was this. There are these many numbers. Similarly, any A in S2 must look like, well, every A in S2 is a multiple of Q, so it must look like this. And till when can this go on? Well, it can go on to this value because this product is exactly equals to n, and we know that A is at most n. And similarly, any A in S3 must look like. So every A in S3 is divided by both P and Q, so it must look like. And when till where can this go on? It can go on till P to the R1 minus 1 to the R2 minus 1 because this product is exactly n, right? So the size of S3 is equal to, okay, let me call this 3. So from from 3 we have that the size of this set, the number of A's in Z 1 to n that are divisible by P or Q is equal to this plus this minus this. And when we put this in 2, we finally get the following. N minus P to the R1 minus 1 times 50 R2 minus P to the R1 times Q to the R2 minus 1. And so there is a minus over here, but there is also a minus over here, so it becomes plus. Yeah, so this is fine. So now let's simplify this. Recall that N1 was this. Okay, so from here we can take our we can take this common and we would be left with P minus 1. And what about here? Here we can take this common. And you, okay, we are taking minus of that common, so you would be left p minus 1. So this is, now we can take p minus 1 common from both to get this. We can simplify further. We can take this, we can take this common, this thing common. That gives us p to the r minus, okay, let me write it, to the r minus 1, q to the r 2 minus 1, and we will be left with what? No, p to the r1 minus 1 and q to the r2 minus 5 commons, 2 minus, so we get, yeah, so this is the value of phi n. And so recall that in class we saw that if n was p times q, then phi n was p minus 1 times q minus 1. Well, in that case, r1 and r2 are 1. So if we put r1 and r2 1 over here, we recover that formula. So this is a generalization of that formula. And turns out you can generalize this even further. So here's the fact. Distinct primes and r1 to rk uh, in n phi of n is p1 to the r minus 1 times p minus 1, p1 minus 1 times p2 to the r2 minus 1 2 minus 1 times p to the r pk to the rk minus 1 times pk minus 1. So as you can see, if you replace p1 by p and p2 by q, you would get the formula that we just derived. So this is the most general formula for phi n, and yeah, this can be obtained using similar ideas. So you can try this on your own as an exercise. Now let's move on to the next problem. The next problem is as follows. Consider the following encryption scheme for 1-bit messages. The public key is G, Q, G, Q, small g, H. Over here, this capital G is a group of order Q, its generator is G, and uh, H is G to the alpha for a private key alpha. To encrypt a bit B, here's what we do. If B is 0, then we pick a beta uniformly at random from ZQ, set C1 to be G to the beta and C2 to be H to the beta. And if B equals 1, then we set we pick beta and gamma uniformly at random from ZQ. Set C1 to be G to the beta and C2 to be G to the gamma. And our ciphertext would be C1 comma C2. So now the problem is, show that if the DDH problem is hard in the group G, then given C1, C2, no PPT adversary can be determined whether 0 was encrypted or 1 was encrypted except with probability at most half plus negligible. So let's see why this is true. So what we'll do is we'll prove this by uh, contradiction. So suppose for the sake of contradiction that there exists an adversary which can break this scheme. Okay, let me call that adversary A. What we are going to do is using that adversary, we are going to create an adversary for the DDH problem. And since by assumption the DDH problem is hide in the group, an adversary A also cannot exist. So what happens in the DDH problem? So the verifier picks alpha and beta uniformly at random from ZQ. Then, okay, uh, it flips a coin uniformly at random. If P is equal to 0, then it sends a DDH tuple. So if P is equal to 0, G to the gamma is said to be an oh, I lost connection. Yeah. And if P equals to 1, then gamma is split uniformly at random from ZQ. And then it sends to the actually yeah, let me instead of calling this G to the gamma, let me call it H. And H is set to be G to the gamma. Okay, so now what does the DDH adversary do? The DDH adversary forwards this to the adversary. If we know the DDH adversary, yeah, let me first compute C1 and C2 and then the DDH adversary sets C1 to be G to the beta and okay, I messed up H. H is different in both cases. Let me call this H prime. And sets C2 to be uh, H prime. Then sends this to A. Now let's say that A says that A would out. What would A do? A would guess whether 0 was encrypted or 1 was encrypted, right? Let's say A says that B prime is encrypted. And then the DDH adversary just forwards B prime to V. Now let's see what the view of A is. So if B is equals to 0, C1 is equals to G to the beta for a random beta. And C2 is equals to H prime, which is equals to G to the alpha beta, which is equals to G to the alpha beta. Why? Because Alpha is the public key and H is G to the alpha. Sorry, alpha is a private key as far as DDH is concerned, and H is G to the alpha. Yeah, so this is G to the beta. That is ADDH, sorry, AC's encryption of 80. Yeah. So this is what happens when B is, this is the how B is a 0 is encrypted, right? G to the beta, H to the beta. It's exactly that. If B equals to 1, C1 is still the same. And C2 is equals to H prime. But in this case, H prime is G to the gamma. That is AC's the encryption of 1. Yeah, so A's view is exactly either the encryption of 0 according to this cryptographic scheme or the encryption of 1 according to this scheme. So what I can write is the following, right? Uh, Probability that ADDH, that is ADDH wins its game. Like it just forwards B prime uh, to it just forwards B prime and it gets from A to the verifier. So I can write this probability that is ADDH guesses B correctly if and only if A guesses B correctly. Now, okay, as we saw here, so when B is 0, A sees the encryption of 0. And when B is 1, A sees the encryption of 1. So A always sees the encryption of B. And since A is an adversary for the encryption scheme, this is exactly the probability that A wins its game, right? Uh, However, as DDH is hardened G, probability that ADDH, which by the way is a PPT adversary because A is a PPT adversary and ADDH just forwards a few things both ways from B to A and A to B. So this is upper bounded by half plus negligible. So P prime equals to B is also less than half plus negligible. Yeah, so we wanted to prove that, uh, yeah, no PPT adversary can determine whether 0 was encrypted or 1 was encrypted with probability at most with probability any more than half plus negligible, which is what we have done because this is exactly the event in which A correctly guesses which bit was encrypted, 0 or 1. Yeah. So this solves this problem. Let's look at the next one. Yeah. Next problem is the following. Consider the following variant of RSA encryption scheme. To encrypt a message M in 0, 1 to the L with respect to a public key N, E, the sender first computes M hat defined as HM concatenated with M, where H is a hash function modeled by a random oracle. So this means that we are in the random oracle model. And the cipher, then what it does is the ciphertext sent is M hat to the E mod N, and the decryption is performed analogously. So, given a ciphertext C, the receiver would compute C to the D mod N. Uh, Once it does that, it obtains H concatenated with M. It drops the initial few bits of H and retains the last few bits of M. So the question is this scheme CCS secure? And the answer to this is very simple. It's no. The scheme is not randomized. And hence, it is not even CPS secure. So it is obviously not CCS secure. Yeah. Now let's look at the 10th problem. So the problem is, suppose that there exists a PPT algorithm to find phi n, that is the Euler Torsson function of n, for a given value of n. Does the RSA assumption also hold in the presence of this PPT algorithm? So recall that in the RSA assumption, recall that the RSA assumption is the following. Um, it says that if a PPT adversary is given n, e, and x to the e mod n for a random x, then it cannot find x, or rather the eth root of x to the e mod n with probability more than negligible, right? So what will show is, no, the RSA assumption is not hold. And what we'll do is we'll basically show that there exists an adversary which can win that game. There exists a PPT adversary which can win that game. So let's see. Uh, the verifier picks N and E. Then it picks Z, picks an X uniformly at random from Z and cross and sends to A. Okay. So what does A do? A does the following. Using and sorry, using N and E compute D such that AD is equals to 1 modifier. That is the modular inverse of, that's the multiplicative inverse of E mod phi n. And this we can do efficiently using the extended Euclidean algorithm. So the first step was efficient because we assume that phi n can be computed efficiently. And finally, it sets y to be, so it got this, it raises this to the model, but this equals to x to the ED model and just forwards y. We saw in class that is the same as x model. So the adversary can win the RSA security. Why? Because in the RSA security game, you are supposed to find an eth root of sorry, eth root of x to the E mod n, and x mod n is one such root, which the adversary has found. So yeah, the adversary can win the RSA security game if it can compute phi n efficiently. Yeah, so if there exists a PPT algorithm to find phi n given n, then the RSA assumption does not hold. And in fact, in the last class, we saw that uh, computing phi n is exactly the same as factoring n. These two are polynomially equivalent to one another. So we could have also, uh, yeah, argued this question using that result. Yeah, so now let's look at problems based on Week 11's content. The first problem is pick the most appropriate combination. In the RHS, we have the CDH. Here, that the CDH problem is easy. D-log assumption is believed to be hard, but the DDH problem is easy. The option C is that the gap DDH problem is believed to be hard. On the right hand side, we have Z cross P for some prime P, Z plus P for some prime P, and elliptic curve groups. So now let's pick the correct combination for all of these ABMs. Uh, okay, the first option is CDH is easy, and here the correct here this should be combined with Z plus P for some prime P, because we know that in this group, in fact, we saw in one of the previous problem solving sessions that in this group, uh, the D-log problem is easy. And we already know that if the D-log problem is easy, then the CDH problem is also easy in that group. So A should be matched to 2. What about B? D-log believed to be hard, but DDS is believed to be easy. Well, we saw in the class that there exists some primes P for which D-log is believed to be difficult in Z cross P, but still DDH is believed to be DDH is easy in Z cross P. So B should map to 1 and C maps to 3. We saw in class that the kept CDH problem is believed to be hard in elliptic curve groups as well as prime order groups of Z cross P. Now let's look at the next problem. So the next problem is the security of which of the following depends on the D-log problem or the D-log assumption. Option A is Peterson's commitment scheme. Option B is Elgamal encryption scheme. Option Option C is Schnorr identification scheme. And option D is none of the above. This should be Schnorr's, not Schnorr. Yeah. Okay, so let's go with all the options. The first option is Peterson commitment scheme. Well, we saw that this is true. The security of the Peterson commitment scheme depends on the D-log encryption, so A is true. Option B is Elgamal encryption scheme. No, we know that we saw that in in class in last week that the security of the Elgamal encryption scheme depends on not the D-log assumption but the DDH assumption. Now we know that there are groups in which D-log is easy but DDH is hard. Sorry, D-log is hard but DDH is easy. In particular, option B over here. So DDH is a strictly stronger assumption than D-log, and because of that reason, we cannot say that that just because the security of the Algol encryption scheme depends on the DDH assumption, it also depends on the D-log assumption. No, we need the DDH assumption for the Algol encryption scheme to be secure. So B is also false. So sorry, B is false. What about C? We saw Schnorr's identification scheme in this week, and we saw that its security also depends on the D-log assumption. So C is true. And what about D? Well, D cannot be true because A and C are true. So yeah, options A and C are true. The security of the Peterson commitment scheme and Schnorr identification scheme depends on the D-log assumption. In particular, well, Peterson commitment scheme is a commitment scheme. So you have two security notions over there, hiding and binding. And in particular, over there, it's the hiding that depends on the D-log assumption. So yeah, assumption. But its binding is unconditional. Yeah. So now let's look at the next problem. The next prob the next problem and also the 14th problem are both about signature schemes. So let pi is equal to gen, comma sign, comma verify be a signature scheme for message space scriptum equals to 0, comma 1 to the n to the 2. That is messages of length n over 2 bits. Consider a modified signature scheme pi prime is equal to gen prime, comma sign prime, comma verify prime for message space script m prime is equal to 0, comma 1 to the n, defined as follows. Gen prime runs two independent copies of gen and outputs vk, sk0, vk, sk1 and sets the verify key vk to be vk0, vk1 and the secret key sk to be sk0, sk1. Then to sign a message m, what the sign prime algorithm does is the following. It takes m and the signing key sk and outputs sigma equals to sigma l, sigma r, where sigma l is obtained by invoking the sign algorithm with message ml and key sk0, and sigma r is obtained by invoking the sign algorithm with key sk1 and message mr. Here, ml and mr are the left n over 2 and right n over 2 bits of m. The verify algorithm works as follows. Verify prime vk m comma sigma l comma sigma r is 1 if and only if either verify vk0 ml comma sigma l equals to 1. That is, sigma l is a valid signature for ml with respect to key vk0, or verify vk1 mr comma sigma r equals to 1. That is, sigma r is a valid signature for mr with respect to key vk1. The question is pi prime secure? So we'll see that it's not secure. And the way we'll do is we'll show that there exists an PPT adversary which can win the signature forgery game. So the signature forgery game, we have a verifier and an adversary. The verifier obtains SK, BK from, oh, am I writing BK? Yeah, BK, SK. Yeah, this is done. And then it sends VK to A. So rather, let me write it like this. This is SK, this is PK. A sends messages, any two mess. Let's say any one message, M1, ML, comma MR. And what does it expect? It expects a signature in return, right? Okay. Now, what does okay? So because of the way the signature sigma L comma sigma R is generated, okay, let me write it. So sigma L is going to be yeah. So sigma L is a valid signature for ML. Sigma L is a valid signature for MR. So both these checks would be satisfied. Now, what does A do? It wants to generate a forgery for a new message. So it generates a new message like this, where M star R is anything other than MR. So this is a new message. And the signature it sends is sigma L comma sigma star R. But sigma star R can be anything, we don't care. Now, what's the probability that A wins? So what's the probability A wins this game? It's the probability that verify VK0 ml comma sigma l equals to 1, or verify VK is 1. Now, okay, we don't know whether this will be true or not, but because of the way that sigma was generated, this would always be true, right? So now this is at least which is equals to 1. So the adversary A can win the signature forgery game with probability 1, and so the scheme pi prime is not a secure signature scheme. So now let's look at the next problem. This is similar to the previous problem. There is just a slight change. So let pi equals to gen, comma sign, comma verify be a signature scheme for a message space scriptem equals to 0, comma 1 to the n over 2. Consider a modified scheme pi prime equals to gen prime, comma sign prime, comma verify prime for message space m prime equals to 0, comma 1 to the n. Defined as follows. Gen prime runs two independent copies of gen and outputs vk0, sk0, vk1, sk1, and sets the verifying key vk to be vk0, vk1, and the signing key or secret key sk to be sk0, sk1. Then to sign a message m, sign prime skm outputs sigma equals to sigma l, sigma r, where sigma l equals to sign sk0 ml and sigma r equals to sign sk1 mr. Where again m equals to ml and m, mr. Ml is the first n over 2 bits of m, and mr are the last n over 2 bits of m. So far this is exactly the same as the scheme in the previous question. The difference is the following. Now verify prime vkm, sigma l, sigma r equals to 1 if and only if both the checks pass. That is, if verify vk0ml, sigma l equals to 1 and verify vk1 mr equals to sigma mr, sigma r equals to 1. That is, if and only if sigma l is a valid signature for ml with respect to key v0 and sigma r is a valid signature uh, for message mr with respect to key vk. Question is pi prime secure? So at first sight, it looks that we have replaced or with and, so it would the scheme should be more secure than the previous scheme. In fact, the attack that we used in the previous question won't work over here. But even this scheme is not secure, and let's see why. So again, we have three, we have A, we have yeah, we have 17, we have 7. Now, instead of asking for a sign on one message, now A would ask for a sign on two messages. And M1 is yeah. So what we will do is for all I2, it's going to send sigma in as and send sigma 1 is to A. Now, A wants to produce a forgery, so here's how A produces a forgery. It defines M star as. So the first block of M star is the first block of M1, and the second block of M star is second block of M2, and sigma star. Now, again, since M star is a new message, also verify VK sigma of 1 as verify VK0 verify PK1 2R is equal to 1. Therefore, probability that uh, Sigforge is equal to 1. Yeah. So A wins the signature forgery game again with probability 1, and so this scheme is also not secure. So now let's look at the 15th question. The 15th question is which of the following options is or are incorrect? The options are any encryption scheme can be used to get an AES. Public key identification schemes only provide security against a passive adversary. Option C is CCA secure hybrid ciphers based on Diffie-Hellman problems require only the CDH assumption to be true. And option D is plain RSA signature scheme is secure. Let's go over all these options. Option A is any encryption scheme can be used to get an identification scheme. Well, this is false. Only public key encryption schemes can give identification schemes. Option B is public key identification schemes only provide security against a passive adversary. Well, this is false. They also provide security against active adversaries if we define public key identification schemes properly. It is there. It is, yeah, that's if we create a secure scheme. Yes. CCA secure hybrid ciphers based on the Diffie-Hellman problem require only the CDH assumption to be true. This is also false because we saw in class that the to prove the CCA security of the uh, hybrid Elgamal encryption scheme, we not only required the CDH assumption, but we in fact required a stronger assumption, namely gap CDH assumption. So C is also false. And D is plain RSA signature scheme is secure. Well, this is also false because we saw in class that any adversary can easily forge a, a signature for a new message using the if we use the RSA signature scheme. So all four options A, B, C, and D are false. So now let's the next problem is so in the class we saw that given a ciphertext C1, C2, of a message M produced using the Elgamal encryption scheme, we can produce a ciphertext C1, C2 prime for alpha times M for any alpha of our choice. So over here C1, we saw in class that C1 remains the same, but C2 prime is different. Now, is it possible to produce a ciphertext C1 prime, C2 prime for alpha times M where C1 prime is not equals to C2? So now we want to produce a ciphertext in which both these components are different. The question is, can we do this? The answer is yes. And here's how. So recall that in the Elgamal encryption scheme, if the secret key is alpha, public key is h equals to g to the alpha. The encryption of M is C, C1, C2. For a beta, choose random from ZQ. Here Q is the order of the group, and C2 is now here's what we can do. Random from ZQ. Set C1 prime to be G to the beta. Okay, set C1 prime to be C1 times uh, G to the gamma, and C2 prime to be alpha times H to the. So now let's see what C1 prime, C2 prime are. So C1 prime is equals to G to the as gamma as split uniformly from ZQ. Beta prime is also random, and C2 prime is equals to, okay, so it's going to the beta times alpha times H to the gamma. So C1 prime, C2 prime is a valid encryption for mm, alpha times n. Now, with probability 1 over, sorry, C1 prime is not equals to C1 because uh, gamma is not 0. Yeah, so with probability 1 over q gamma would be 0. So with probability 1, q minus 1 over q gamma won't be 0. And in that case, C1 prime and C1 would be different. So with probability q minus 1 over q, we would have created a valid ciphertext for alpha times m, which satisfies this condition. So yeah, this is possible to do. Okay, so that's all that for today. Uh, we can meet on 4 to 6 this Saturday as usual for the 11th problem solving session. Yeah, till then, bye.